Hi everyone and welcome to the internet. So what we're going to be doing in today's triple chemistry lesson is having a look at the effect of catalysts on the rate of reaction. So to start us off, we've got our starter questions based around our previous lesson. So up to grade 5, question on the left, over grade 5 is your target, it's the question on the right. So get those answers written in your books for me. I'm going to give you about 2 minutes to do that today. Okay, let's check those answers then. So for up to grade 5, the pattern that we see is that as the surface area increases, the rate of reaction increases. Give yourself a tick if you got that, because that's where it needs to end, because it was a describe, so we say what we see in terms of the pattern. For those of you on the grade 5 and up, this one was an explain, so this is we say what we see and why we see that using science. So first mark, if we said as surface area increases, the rate of reaction increases. Second mark is for saying that there are more particles exposed to the other reactant. And our third mark for saying that there are more frequent collisions. So add your score up out of 3 for the grade 5 and up, and obviously your score out of 1 for the up to grade 5, and write that in your book for me. One of the phrases that we have met throughout our course at earlier stages is this word catalyst. So what I'd like you to do then is write down what a catalyst is. And then just remember that when we're talking about these catalysts, they are specific to a reaction. So write down your definition of what a catalyst is, and then the second sentence in your books for me. Just going to give you about a minute and a half to do that. Let's check to make sure we all remember what a catalyst is then. Hopefully we've said that a catalyst is a chemical that speeds up a reaction. You can give yourself a tick for that part if you got that right, without being used up in the reaction. So 2 ticks available. First one for a chemical that speeds up a reaction. Second for saying it's not used up in the reaction itself. So this is our key definition for a catalyst that we really have to remember. So it's a chemical that's going to speed up the rate of a reaction without being used up in the reaction itself. And the other key point we need to remember is that they are specific to a given reaction. So we can't use one catalyst for every reaction. We have to have a specific catalyst for a specific reaction. And if we want to catalyze a different reaction, we're going to need a different catalyst to do that. So again, this is one of those things that we normally do an experiment in the classroom. So again, we get to look forward to all these experiments when we are finally back in school. But I have found another video for you about one of these actual demonstrations. Now, I'm not going to lie, the guy that's doing this is a little bit strange, but it's a demonstration we can watch anyway, so I apologise for his slightly interesting humour at times, but the experiment side, it's good. So, what I want you to do is you watch this demonstration, is write down your observations in your books.
So, earlier today I was digging through the vast deserts of Arabia, and I found an ancient bottle. When I went to polish it off, a genie came whooshing out of the top, and he told me he'd grant me 3... You know what? I'm going to spare you. Today we're doing the genie in a bottle experiment. Alright, let's science. The genie in a bottle experiment is a decomposition reaction. A decomposition reaction occurs when one reactant breaks down into 2 or more products. In its most basic terms, what this means is if I have compound AB, the reaction breaks it down into A and B. Not ABC, not AB plus C, not BD plus F. We had AB and now we have A, and we have B. Like your couple friends who broke up last month, they're still there. They're just not together anymore. A good example of a decomposition reaction is the breaking down of hydrogen peroxide, chemical compound H2O2, from hydrogen peroxide into water and oxygen, and the breakdown of water to hydrogen and oxygen, which is not too far off from what we are doing. In fact, it's exactly what we're doing. Well, the first part anyway. The oxygen parts off as, well, oxygen. So long, oxygen. And the water is still water, it's just in a different state. It's expunged as water vapor. The big difference here is that we are using a catalyst in this reaction. And because we are using a catalyst, this experiment may also be referred to as a catalytic decomposition experiment, because it is a decomposition reaction, but aided by a catalyst. Now, when we refer to a catalyst, what we mean is a substance that increases the reaction rate, as in the time it takes a reaction to happen, but is not consumed in the course of the reaction. It's important to note that last part, not consumed in the course of the reaction. In the case of any reaction involving a catalyst, the reaction would happen on its own with or without the catalyst. It's just that the catalyst makes it happen way faster. Kind of like fast forwarding time so you can see the reaction happen really fast. But you don't age, like in that one Adam Sandler movie. Now that I think about it, you could say, like in that one Adam Sandler movie with just about anything. So, click. I was talking about click. Okay. So now we have a catalyst in this experiment, but what is our catalyst? Sodium iodide, in solid form. We'll get to why in a second. First, let's explain why sodium iodide in the first place. The answer is that sodium iodide oxidizes the hydrogen peroxide, allowing the oxygen to free itself from the tightly bonded grips of the hydrogen peroxide. It is a catalyst, so the amount does not really matter. The only reason to increase the amount is so that the initial reaction may be quicker. The extent of the reaction will just keep going until the peroxide's all used up. So it's doing something that would have already been done anyway. It's just speeding it along. Like when a boyfriend doesn't want to be shopping with his girlfriend. Believe me, she'll still do all of the shopping she came to do. She just may have to make some decisions and try things on a little faster than if he wasn't there. So I guess we could say here that the boyfriend is the catalyst. Now that we got all the players in this game, let's get to the actual experiment. I'm going to put on my chemistry teacher hat here and give you the full script. Okay, we have this bottle here. It's wrapped in foil. There's a genie in this bottle and he wants to get out. To release him, you'll just pull this cork and he will come out and he'll grant you wishes. Before the genie is released, I'm going to need a student, you're fine, come on up here, to come and touch the bottle. They come up, they feel it. Is this cold? Yes, it's cold. Room temperature, whatever. The bottle is currently cold. After that I say, kazalazazam, and I pull the cork. The vapor will start to shoot from the bottle. I will say, oh no, this genie's really mad. Everybody hit the deck. I'll flick the lights on and off. I'll turn on my lasers. Okay, I'm not trying to cause a riot in the classroom. I'm just trying to make a point. In all reality, the water vapor will go and keep going and keep going. And when it finally runs out of steam, pun intended, I'll ask the same student to come up and touch the genie bottle. He, she will. Now it's hot, not cold, not room temperature. Then I will go through the same experiment again, but without the aluminum foil so the students, and of course you, my lovely audience, can see what is really happening. Just 1 scientific second, Batman. Sodium iodide is white. This powder is gray. What gives? Well, actually what we're talking about here is sodium iodide. What we're looking at here is manganese dioxide. Both can work as a catalyst for the genie in a bottle experiment. I've already started talking about sodium iodide, so I'm just going to keep on with that. Just know what we're looking at here is manganese dioxide. You can chew me out in the comments. This produces the same type of reaction, a decomposition reaction with a catalyst. Before you even step foot into my lab, I took some toilet paper and I put the powder form sodium iodide, our catalyst, in it. Tied it off with some string and closed the string in the stopper, hovering ever so slightly over the hydrogen peroxide so that the experiment will be triggered when I open the stopper, therefore dropping the catalyst into the hydrogen peroxide, creating the steam and making it look like it comes alive when the stopper is removed. And that is why we wanted our sodium iodide in powder form, which by the way looks really cool when it hits the hydrogen peroxide. Do we have footage on that? Yeah, roll some footage on that. Why would you deprive anyone from seeing that twice? So I'm going to show it to you again. Rewind the tape. So satisfying. We actually have a satisfying video you should check out, by the way. We gotta get back to this. So what we really have here is an experiment that's part magic trick, part chemistry experiment. Wait, what? Chemistry isn't magic? The only difference between chemistry and magic is eyeliner, children. Okay, hold up. True. Chemistry isn't magic, but it uses a few pages from magic to prove science. First of all, we have the member of the audience bit, wherein someone who could never be in on the trick confirm what is happening, both with the exothermic reaction and the pulling off of the top. And it uses parts of the experiment you can't see, namely the sodium iodide, our catalyst, being dropped into the solution without the audience knowing that it sets the experiment off into high gear. So between the water vapor and the aluminum foil, I'd call that the smoke and mirrors here, wouldn't you? And let's not forget that while a volumetric flask is the best instrument for this experiment, it does look a whole lot like a genie bottle. Well, at least the closest thing you can find in a lab, especially when covered with aluminum foil. But remember the audience participation? The student who comes up and verifies the flask is indeed hotter after the reaction? He, she is not like the lady who gets sawed in half. He, she is not a plant in the crowd to hoodwink us. The flask is in fact hot, which means it is, you guessed it, an exothermic reaction. Exothermic reaction meaning heat is a byproduct of the reaction. Usually exothermic reactions indicate that electrons are transferred from one atom or molecule to another. That is not the case here. In fact, it generates so much heat that the water, when decomposed out of the hydrogen peroxide, does so as vapor, not a liquid. Think about that. When you see water vapor, it's like when your grandmother's making tea. The water is that hot right now. But to note, it's not just water vapor shooting out of that genie bottle, it's also oxygen. Remember our couple that is no more? Well, they may no longer be an item, but they're going out the same door. The door here being the opening in the volumetric flask, never to go on a date together again. Although they'll probably find someone much better suited to them down the road. So there you have it, the genie in a bottle catalytic decomposition reaction, boyfriend and girlfriend who are no longer together, magic trick in the chemistry lab, experiment. Wow, that is a mouthful. Maybe that's why we just stick with genie in a bottle. That's way easier to remember. Leave us a like right there or wherever it is if you like the video, and tell me in the comments what you would do with 3 wishes.
So in terms of the reaction you would actually be doing as a practical, then again we've got the method here. So you'd actually be looking at breaking down hydrogen peroxide with bits of potato, because the potato actually contains a catalyst to this reaction of decomposing the hydrogen peroxide. So as usual, if you jot down those points for me about how to carry out the method in your books, then we'll be able to use that in the future. So the first thing we're going to do is measure 25 centimeters cubed of hydrogen peroxide and place it into our conical flask. We'll set up our upturned measuring cylinder filled with water as usual, and then we're going to add 1 cube of our potato to the conical flask and start timing. After a minute, we record the amount of gas made, and then we repeat the experiment using 2, 3, 4 and 5 pieces of potato. So I'll leave this up for a couple more minutes for you to write down those methods for me. So thinking about the method we've just written down, there are 3 questions on the screen for you to answer in your books. First one, what was the independent variable? Second, what was the dependent variable? And third, what variables do we need to control in the experiment? So answer those in your books for me. I'm going to give you about 5 minutes to do that. Let's check those answers then. So obviously mark your work as we go through these. The independent variable, first of all, is the amount of catalyst. You might have described that as the amount of potato in this case. The dependent variable is the volume of gas that we're producing, and the controlled variables, the volume of hydrogen peroxide, the concentration of hydrogen peroxide, the temperature, and then a whole range of different things about the potato. So the age of the potato, the type of potato, the size of the potato cubes. We could have said if there was skin on the potato, a whole range of different things there. If you had any others, then let me know in the chat window and I will obviously tell you if you're right or wrong with those ones. Otherwise, tick all the ones you got right, and obviously if you got the independent or dependent variables wrong, make sure we remember independent, the thing we are changing, dependent, the thing we are measuring. So add up your scores for me and write those in your books. So in your books, thinking about the demonstration we've just watched, see if you can finish off the conclusion here. I found that, and then tell me what you think you'd find by adding more pieces of potato, what would happen in that experiment to the rate of reaction. So just a minute to get that answered in your books. The next thing we need to know is why. We need to be able to explain why it is that adding a catalyst is going to increase the rate of a reaction. Now, if we think back to the work we did back in C3, then we drew these things called our reaction diagrams or reaction profiles. And you can see one at the bottom of the screen there. So on our x-axis is the progress of the reaction and the y-axis is the energy. So we start off with that horizontal line which is labelled hydrogen peroxide. So that is the energy stored within the reactants. And then on the right hand side you can see there's a line labelled water and oxygen. That is the energy in the products. And if you remember, what we said is that there's a little bump which is going to be the activation energy. So the amount of energy we've got to supply to the reactants to cause the reaction to actually take place. And then that connects those two horizontal lines. What we can see is on the diagram I've given you here, then we've got two of those little bumps in the middle. Now the reason for that is we've got the activation energy with no catalyst, which is the red one, the top one. And what we can see is we need quite a large amount of energy in order to actually start that reaction. So it's got quite a large activation energy without a catalyst. Whereas when we add a catalyst, what it does is it creates a different reaction pathway. And that different reaction pathway has a lower activation energy. So we can see the size of the bump there in the blue line is much lower than the one without the catalyst. So that tells us we need less energy to be supplied to the hydrogen peroxide to cause that breakdown. So what we will see is the rate of reaction will be quicker because we're actually having a much lower activation energy. So that means it's easier to exceed and therefore the reaction is going to happen faster. So if they ask you why adding a catalyst, or to explain why adding a catalyst will change the rate of reaction, it's because it provides a different reaction pathway with a lower activation energy. So I'd suggest you get that sentence written down and copy that little diagram with the labels. So I'll just leave that up there for another minute because I expect some of you already started on that. So to finish off today, then I've got an example of a 6-mark question for you to have a go at. So the rate of reaction between marble chips and hydrochloric acid can be increased by using smaller chips. Another method of changing the rate of a reaction is by adding a catalyst. Describe and explain using the reacting particle model 2 other ways the rate of reaction could be increased. So get those answers written in your books. I'm going to leave the question on the screen for about another minute, but if you think you're going to want the question up for longer than that, then obviously hit pause on the video now. As always, you can find the answers to the plenary over on my website, sciencewright.weebly.com. You'll also be able to find that under the Internet tab. Just select the week that we're in, and then you'll be able to find things like the lesson PowerPoints, the answers to the plenary, any additional work, and if there's any little experiments I thought you could do at home, then they're there too. So have a look and get using that.